Hello, everybody. Thank you for tuning in to my presentation on event-scale sediment yield modeling of agricultural isolated wetlands in Southwest Georgia. My name is Coleman Barrie, and I'm a first-year PhD student in the Civil and Environmental Engineering Department at Auburn University. This is the first chapter of my PhD dissertation and is a part of a larger project in cooperation with the Jones Center at Itchaway and the Crop and Soil Sciences Department, investigating wetland mitigation of non-point source agricultural runoff. A little roadmap for this talk: I will be discussing why geographically isolated wetlands are important and the ecosystem services they provide, as well as the data collection, analysis, and modeling approaches I will be taking. And lastly, I will highlight currently my favorite site and introduce a feasible management solution to enhance ecosystem services in some agricultural isolated wetlands. Without further ado, thank you for tuning in once again, and here's the presentation. Welcome to event-scale sediment yield modeling of agricultural isolated wetlands in Southwest Georgia. This project, I'm Coleman Barrie, and this project is done in cooperation with Dr. Francis O'Donnell, Dr. Stephen Brantley, Chloe Eggert, Dr. Matt Waters, and Dr. Steve Galladay. So what are geographically isolated wetlands? They're unique in that they form in subtle places caused by depressions in the landscape. They lack persistent surface water connection to lakes, rivers, or other wetland systems, and their water level can fluctuate greatly throughout the year, as can be seen by these two pictures of the same wetland at two separate points in time, separated by about 6 months. Despite the term isolated, they are far from hydrologically isolated on the landscape, as wetlands can commonly be connected through subsurface flow paths to other surface water bodies, and can also be connected through surface water flow paths during exceedingly wet conditions. Geographically isolated wetlands provide many valuable ecosystem services, such as the addition to biodiversity, flood protection through peak flow rate, attenuation and increased lag time to downstream water bodies, and water quality improvements, as the retention of water can allow settling of particulates over time. Also, geographically isolated wetlands contribute to aquifer recharge, as water can vertically infiltrate through the low conductivity clay layer. It should be noted that geographically isolated wetlands are no longer protected by the federal government, and that they're also called GIWs, isolated wetlands, and depressional wetlands. Wetlands in agricultural settings have a trade-off of ecosystem services, maximizing their water quality improvements by storing harmful agricultural runoff. And the major goal of this study is to better understand sediment and nutrient dynamics in a variety of geographically isolated wetlands to guide management and restoration efforts. This study addresses two main research questions. How do water level and water quality vary from agricultural inputs across a representative sample of geographically isolated wetlands? And what are the sedimentation rates of agricultural wetlands in the Dougherty Plain or the Southeast Coastal Plain on the storm event scale? Many sedimentation studies have been performed in other wetland systems, similar wetland systems, such as the Playa wetlands and the Prairie Pothole region. So it'll be interesting to compare this data to different parts of the countries that contain agricultural isolated wetlands. My study is located in the Dougherty Plain, which is a physiographic region of the Apalachicola Chattahoochee Flint River Basin, or ACF Basin. More specifically, in and around the Jones Center in Baker and Mitchell County, right on the Flint River. This region is special because of the karst, superficial limestone bedrock, also known as karst, in low topographic relief, which creates many isolated wetlands and high connectivity between surface, all water bodies. We have a total of 6 study wetlands in this project, 4 agricultural sites and 2 reference forested wetlands. When selecting the agricultural sites, we focused on 4 defining traits: watershed size, watershed shape, position with reference to the center pivot irrigation field, and the 2 characteristics were embedded and adjacent, to analyze the differences in sedimentation rates as well as watershed slope, as slope is highly influential to runoff and associated sediment transport. Here's a picture of OS 79 in the Bush Herd Field, which is this site right here. Two forested wetlands were selected at the Jones Center at Itchaway, which was the perfect place to find a reference wetland that is in a relatively undisturbed region. And the Jones Center has numerous wetlands, and thankfully we were able to find 2 wetlands that were similar in size to the agricultural wetlands. And here we focused on differences in shape and tried to maximize the forested watershed. Here's a picture of wetland 37. As you can see, there are different ecosystem services that are provided in these reference wetlands. The biodiversity is pretty incredible. We're collecting a lot of data in order to calibrate specific sediment yield models for each of the study wetlands. These include, the data collection includes sediment traps within each wetland, rain gauges measuring the rainfall at each site, water level loggers inside the wetlands, monitoring the changes in water level with respect to evapotranspiration and storm events. We collected upland soil cores in the watershed to understand the organic matter content and textural and the particle size distribution of the soils for model input. We will be using a data-driven approach to understand the curve number for the site and changes in the curve number by calculating the change in volume in the wetland with respect to each storm event. So therefore, we need to have a good idea of the wetland bathymetry, which we will be trying to pick up during a dry time using terrestrial LiDAR. I'm also using LiDAR with 1 meter resolution provided by MEON, which is the National Ecological Observatory Network. This is publicly available data, and I'm also using a USGS LiDAR data set. But it is great for model input as it gives very accurate topographic information for slope, flow path length, and watershed delineation. Wanted to highlight the sediment traps because we did a little bit of design on them. Originally, Chloe and Matt at the Crop and Soil Sciences Department put these together, and they've been great so far. They consist of a PVC post with a wooden cross section. As you can see here, and 2 bottles are attached to each side of the post, and they're bashed into the ground so that the top of the bottle is about 30 centimeters from the surface to prevent recirculation of wetland material in the bottom of the wetland from entering the bottle. But the bottles are capturing incoming sediment from the surrounding watershed. And I collect them every month and then determine the amount of dry sediment in each bottle. The sediment traps are being used to calibrate the MUSLE model, which is the event scale sediment yield model. And we're also investigating preferential versus uniform settling, because in order to understand sedimentation in the wetland, we're extrapolating the amount in each bottle by the wetland surface area. So we've currently installed all of the equipment to collect data, and we are routinely checking the data. It's pretty fun walking out into the water to grab these traps. We have a few data analysis methods that I'm doing. In order to understand the watershed characteristics, we're analyzing the LiDAR data as well as soil samples throughout the watershed. We're understanding changes in wetland storage volume and quantifying the runoff volume through water level loggers in the wetlands and the LiDAR data set. And we're understanding sediment yield based on the amount of dry sediment in the bottle traps. In order to quantify the dry sediment in this bottle full of water, I found out the best method was to allow the bottles to settle over a couple days, then carefully decant the relatively clear liquid on top and perform TSS, or total suspended solids, on that liquid, and then scoop out the remaining clay, or they're typically very fine particles that have accumulated in the bottom of the bottle, and then place that in a drying oven until a constant weight is achieved. In order to calculate sediment yield on an event scale, using the MUSLE equation, which is the modified universal soil loss equation, USLE measures sediment loss on an annual basis in units of tons per hectare per year, and MUSLE replaces the R factor with storm event specific parameters, surface runoff volume and peak flow rate and the area of each, and you calculate this for each subbasin. And by placing a storm event parameters for the R factor, you can estimate the sediment loss from a single storm across a watershed. And this is important to note that the MUSLE output is sediment loss from a field, but I am interested in sediment accumulation in the wetland. So the amount that reaches the wetland and our value for after extrapolating the sediment trap, the dry mass of soil in the sediment trap will likely be less than the MUSLE prediction, as less sediment reaches the outlet point than is removed from the field as the sediment is lifted and dropped. So alongside the storm-specific parameters, in the storm-specific parameters, we're considering the SGS curve number method in TR55, and the other parameters are the same as the universal soil loss equation, which we're diving into detail, understand the soil erodibility factor, which is entirely based on particle size distribution and organic matter content, and the crop cover factor, which is based on land cover and the status of the crops, or that are currently, as the land cover is constantly changing throughout these agricultural watersheds. The farming practice factor, which is determined by the farmer's ability, or by the farmer's decision making, and the LS slope length factor, which can be determined pretty accurately through LiDAR, and then a coarse fragment rock factor, which can be found through the soil samples. So in order to guide decision making, we performed a local sensitivity analysis in order to find the most influential inputs, or the inputs that were most influential on the model output. And so what I did was put the MUSLE equation in terms of all the input factors using the storm event, SES curve number and TR55, and found that slope was by far the most influential parameter. So I feel pretty good about that, since we have really accurate data through the LiDAR. And everything else we can test for pretty well, like rainfall, slope, sand, silt, clay percentage, and the watershed organic matter content. The LiDAR is providing really good watershed delineation to be confident about our drainage area, and the flow length, we can be pretty confident about that. The only parameter that would be highly influential to model output that we're the most uncertain about is the curve number. And the influence of land cover in the sensitivity analysis is probably underestimated, as the C and P factors are not currently considered. But we want to put a lot of attention into how we calculate the curve number, which is why we are using a data-driven approach by solving this empirical formula by back solving it through changes in runoff volume before and after a storm event. So we can understand infiltration by calculating the change in runoff volume for a certain storm event. And if we can pick up good wetland bathymetry through this terrestrial LiDAR, we can be pretty confident about the shape of the wetland, and therefore, quantify the amount of water reaching the wetland after a storm event. So I'm excited to see how that works and have the opportunity to work with terrestrial LiDAR and emerging technologies, and that can be really beneficial to watershed studies. So my favorite site so far is wetland OS80, which it is unique in the sense that it has 3 distinct segments created by 2 center pivot berms. And these berms were installed to facilitate center pivot irrigation movement around the field. But one interesting characteristic is that in these specific berms, we were not able to find any culverts, which can be common in larger berms, but this wasn't necessary for the structural integrity of the berm. But it has implications to the ecosystem services and overall health of the wetland. I converted the raster, the LiDAR data set, into topographic lines, topographic contours, and delineated the watershed for each segment. And I found that the outer portion, OS8, which I'm calling OS80C, contains about 20% of the wetland area, but it receives about 59% of the drainage area. And I'm really curious about the implications to this. It appears that water can seep through these berms, as we have a water level logger in each segment, but the sediment, the sediment remains. And I've seen that so far in the first couple of data collections where we have bottles or sediment traps inside each segment. So, one feasible management solution that would be pretty cost effective is installing culverts inside the berms of that are traveling throughout wetlands, and how much should we value this inter-wetland connectivity, and what are the benefits and harms of subdividing a wetland into 3 parts? It's something that I hope to explore in the future. So far, we've had some very basic conclusions, but they've been interesting to see. Through the data, a couple rounds of data collection, we found that the wetlands can be very different, and especially the water quality inside these wetlands. And they're largely subject to their surroundings, and now the land management decisions of the landowners surrounding these wetlands. They create, and these decisions by landowners are creating different environments that provide different ecosystem services. So if you have any similar work or interests to anything I've spoken about today, I would really like to connect. So please reach out. A couple topics that I'm going to explore on the near horizon are the influence of berms inside wetlands, terrestrial LiDAR scanning for wetland bathymetry, any work with drones. I think the technology is really cool, and MATLAB analysis of time series, rainfall, and water level data loggers specifically, and the calibration of hydrology models in MATLAB, as in order to calibrate a sediment yield model, we first need to calibrate the hydrology, and this is new to me, so I'd really like to discuss my research with anybody who is interested, and I created a domain specifically for this, so please reach out and email isolatedwetlands@gmail.com. The progress we've made so far would not have been possible without the help of many staff at the Jones Center, including Stribling Stuber, Chelsea Smith, Brian Clayton, Jamie Rogers, and Andrew Arco. And also through funding with the USDA. And thank you for providing the funding to make this project possible. And thank you so much for your time. And I hope to speak with some of you in the future. Thank you.